Okay, so I want to explain problem 69 in the book, which is a tricky one, and I think it's driving in a good concept, but it's fairly difficult to follow through with the way the wording is. So I'm going to go over that. But before I go over that, we haven't talked that much about integrals or even derivatives yet. So I just want to take you through a quick example. Let's say we have an easy function like y equals x, and instead of calling it y equals x, I'm going to call it f of x equals x. And that's just this basic line. And then I'm going to define another function, g of x, that's an integral. And so now my integral is going to go from 0 to x of f of x dx. Okay, so now the original function, if I think of like what this looks like in a table, when x is 0, 1, 2, 3, f of x is just the same number. If I think of what is g of x is that area in between 0 and x. And so since it's a triangle, it's 1/2 x squared. So if I plug in 3 for x, I should get 9 divided by 2, which is 4.5. But there's an issue with the way that I wrote my function up here, because now I have x representing the limit, which it's a variable and it's the limit. It's like the right edge of my integral. And it's also representing something within the function. And so what this is important to understand is that this part, this number that goes inside of a function is not inside of an integral, is not actually a variable. It's like a counter. It's like the summation number that takes on all the different values between the left and the right edge. Okay, so for this, if I define a function x to be the variable, I cannot write it so that inside this expression or the integrand that I have the same variable as the one that I used in one of the limits. Okay, and what this t does, it's going to take, in this case, it's going to go 0, and then it's going to take on every single value between 0 and x, and it's going to take the height of each line of the function between 0 and x. Is going to add them up together, and it's going to get the total area, which is the same, which is what the integral represents. There. So in problem 69, we've got this picture, and we're thinking of a function, and we want to know this about the function. This whole, some kind of derivative of an integral. And so if we just kind of follow through the example, it says start by examining the dark gray rectangle in the diagram. As h approaches 0, what does the dark gray rectangle represent relative to the integral from a to x of f of t dt? So they're asking, what does this represent as h approaches 0? And what they're trying to show you is that as h approaches 0, this thing gets infinitesimally thin. That represents just f of x. Now it says write two different expressions that can be used to calculate the area of the dark rectangle as h approaches 0. One expression should use a familiar geometric formula, and the other should use an integral. Do not forget that each expression must include the limit h approaches 0. Note, neither of these limits should be evaluated yet. Okay, so one, just looking at this picture, just looking at that picture right there, geometrically, what does that equal? That equals h times f of x. And another way to describe it using an integral would be the integral from x to x plus h of f of t dt. And now what they're telling me is I want to evaluate both of those as the limit of h approaches 0. And then I guess I took care of part C. Since both expressions in part B represent the same area, combine them into a single equation. Now D, knowing that f, capital F, represents the antiderivative of lowercase f, use this method developed in problem 66 to evaluate the integral part of your equation. Okay, so that's talking about the right-hand side here. I can evaluate so if I want the integral from a to b of f of x dx, this is how we define these functions, would be f of b minus f of a. That's how we define that operation, the integrator. So this is going to be limit as h approaches 0 of capital F of x plus h minus capital F of x equals the limit as h approaches 0 of h times f of x. Algebraically maneuver the equation so that one side represents the derivative of the integral from a to x f of t dt in limit form. Recall that a limit as h approaches 0 is often used to define a derivative. Be prepared to explain the result to the class. Okay, that's confusing. But what they're telling us to do is try to evaluate this so that it makes sense in some way related to what we already know. So how about if I divide both sides by h? Then these things cancel, and I get limit as h approaches 0 of f of x is equal to limit as h approaches 0 of f of x plus h minus capital F of x divided by h. And so now, hopefully, one of these sides, the right-hand side here, is starting to look like something that you already know. And of course, the left-hand side has a limit as h approaches 0, but there's no h in the expression anymore. So the limit as h approaches 0 is the same as just f of x. And if I think of what am I saying, well, this is the formal definition of the derivative of capital F of x, which means that lowercase f of x is the derivative of capital F of x. And this is, in essence, your fundamental theorem of calculus, I believe. And another way to think about it, I think, is just what's this thing? This expression is saying we have an integral, right? The integral goes from a to x. This part right here is saying, by how much does that area change when x changes slightly? So this part right here is what you think of as dx. And so I'm saying if I move the limit, the right-hand limit, just an infinitesimally small amount to the right, just a sliver, by how much does that volume, or not the volume, does the area of the integral change? And it should make sense that as you move it to the right by just a sliver, like if this gray rectangle was just a single line, then the answer would be f of x.